network itself, I can't access any of it. So if you do have any other questions on 2.6, just let me know. We can go over it. But the last bit wasn't too bad. If you do get a chance, go on and watch it. I did post like one of the homework assignment problems, how to do it, so that y'all can see that. And it was especially with functions that we looked at on the graph where it was this, and then we're transforming it in some way, shape, or form, and looking at how to specifically transform or apply the transformation to that function. Now, one of the first two things we're looking at, or one of the things we're looking at today, is symmetry, or to the x, y, and origin. Now, these here are tests for symmetry. Now, we say the equation is symmetric with respect to the y-axis if substituting negative x in for x in the equation results in an equivalent equation. All that's saying is if we substitute x with negative x, we change x from positive to negative, simplify it, and we get the original equation, then it's reflected. Sorry, let me try that sentence one more time. Then it is symmetric with respect to the y-axis. If we do the same thing, but this time we're replacing y with negative y, and we get the same equation we started with, then it is symmetric with respect to the x-axis. And if we do it with both, we switch y to negative y with y, and negative x with x, and we get the original equation we started with, then it's symmetric with respect to the origin. Now that seems a little weird what we're trying to do, but if we look at the first one here, a, y is equal to the absolute value of x. So if we want to check to see if it's symmetric with respect to the y-axis, well, we're going to replace negative x, or x, with negative x. So here, what we're going to do is replace this x with negative x, and then simplify. Now, pure mathematics, or if we look at it in the pure mathematical way, we could say that this here is the same as negative 1 times x, which is the same thing as saying the absolute value of negative 1 times the absolute value of x. Well, the absolute value of negative 1 is positive 1, leaving us with just the absolute value of x. Now we can do this partially because, one, there's nothing being added to x, especially in our original equation. We don't have the absolute value of x plus 1, so replacing it with negative 1 doesn't really change anything. But also, did we get back to the original equation? Yes. So what we can say is that this here, this function, is symmetric to the y-axis. It's symmetric to the y-axis. Really, we're just saying we can reflect it across the y-axis. Any point on the right side of the y-axis is going to be similar to the left side. The only thing is that the x values are going to be flipped. Is a value for when x is 1 will give us the same value of y when x is negative 1. So if we go math, absolute value of x, and graph it, we see that we have a mirror image on either side of the y-axis. So it is reflective or symmetric across the y-axis. Now if we did the same thing, but for x-axis, we said negative y is equal to the absolute value of x. Here, again, for any equation, we need y by itself. We need it to be positive. So we can multiply both sides by negative 1. We can divide both sides by negative 1. It will give us positive y again. But here we have negative absolute value of x. Are these the same? No. So it's not symmetric to the x-axis. It's not reflected across the x-axis. And if it fails for 1, it's not going to be possible for the origin, because origin is really going to be reflective or symmetric to both x and y. If we have both, it's most likely going to be reflective across the, symmetric across the origin. Questions on this here? Okay. Let's look at B, which is our x is equal to y squared minus 4. And whenever we replace one, so we can start off like we did the first one, replacing x with negative x. And what we're trying to do, and I really didn't say this on the last one, is we're trying to get it back to what the original equation looks like. So our original equation here is x equals y squared minus 4, yes? The x is positive, the x is by itself. Here, our x is negative. So if I wanted to make it positive, I would divide everything by negative 1, which tells us x is equal to, the x's do match now, yes? But y squared divided by negative 1 is going to be negative y squared. Negative 4 divided by negative 1 is plus 4. Are these two equations the same? No. So what that tells us, it is not symmetric to the y-axis. It's not going to be reflected across the y-axis. So that doesn't work. So the next one we can try is see if it is symmetric across the x-axis. And if it's symmetric across the x-axis, then replacing y with negative y will give us the same equation. And we'll simplify any place we can. Because negative y squared, negative y times negative y. Well, a negative times a negative is a positive, and y times y is y squared minus 4. Are these two equations the same? Yes. So this is symmetric to the x-axis. About the right y, but it's symmetric to the x-axis. Because when we replace y with negative y, we're talking about the x-axis. When we replace x with negative x, we're talking about the y-axis. Questions on these here? Questions on any of this so far? All right. Now this one here, we want to determine if, and they gave us the graph, if it is symmetric to the x, y, or origin. So we can look at the y-axis first. So the first thing I can do to see if it is symmetric to the y-axis is replace x with negative x. Well, negative x squared. Negative x times negative x is going to be positive x squared plus y squared equals 9. Is that the same as our original function? Yes. So we can say it is symmetric to the y-axis. As when we replace x with negative x, we're talking about the y-axis. So we can say it's symmetric to the y-axis. Would we agree with that there? Yeah. Now we can also test for x-axis. And we test the x-axis, we replace y with negative y and do the exact same thing. We simplify it. Well, negative y squared is going to become y squared. And is this the same as our original function? Yeah, so it's also symmetric to the x-axis. if it is symmetric to both the x and y axis, there's a good chance it's going to be symmetric to the origin. If we test symmetry to the origin, we replace x with negative x, and we replace y with negative y. We replace both. And as we've seen already, negative x squared is just x squared. Negative y squared is y squared. And is this the same as our original function? Yeah, so we can also say that this is symmetric to the origin. Make sure I spelled that right. O-R-G-I-N. Yep. Oh, there was one more I. O-R-I-G-I-N. So it's symmetric to the x, the y, and the origin. So really kind of a giveaway that it is symmetric to the origin is if both x and y work, the origin is going to work. Questions on this here? For the most part, yes. Not always. There are going to be some that don't work. Because really the origin is telling us that it's symmetric across the line, y equals x. This here, kind of line. That's across this line, y equals x. That it's going to be the same on either side. That the point here is the same distance as the point here. So there are some cases where we can get away from that. It doesn't work as well. Especially if we looked at, say, a circle kind of up here, is not always necessarily going to be across this line. Because as we look at this here, well, there's no point reflected across this line. So it wouldn't be reflected across the origin. But it is still across the y-axis. Can we see that there? Because it's still on one or the other. Because once we start getting away from the y-axis or x-axis, the likelihood that they're symmetric to one or the other goes away. Let's see here. So I'm just going to add this in. Let's say x cubed. Or instead of f of x, we can say, actually, let me use, y equals x cubed. If we replace x with negative x, negative x cubed is actually just negative x cubed. Because a negative times a negative is a positive, times a negative is a negative. So we get this here. So are these the same? No. So that tells us it's not symmetric to the y-axis. Now we can replace y with negative y. Negative y is equal to x cubed. To get y by itself, we divide both sides by negative 1, telling us y is equal to negative x cubed. Okay? Okay. If you get a chance. Sounds good. If you want to grab the note sheet and review sheet, they're right there. Hope you feel better. Are these the same? No. Now this is kind of one of the interesting cases because I said before, and I'm going to contradict myself, that if x and y work, then it's going to be reflective across the origin, yes? Now let's try this one here. I'm going to replace y with negative y, and I'm going to replace x with negative x. Here we get negative y. Negative x cubed, we already saw is negative, it's going to stay negative x cubed, yes? If I get y by itself, we get y is equal to x cubed. Are these the same? So this here is not symmetric to x or y, but it is symmetric to the origin. And this is kind of the funny one out. Does that make sense? Now, I'm going to change it just a little bit. I'm going to say plus 1. And as we talked about yesterday, or the video we did that y'all didn't get to see, but on Friday, when we add something to the end, it moves the function up or down. So all I'm saying is I took the cubic function and moved it 1 unit up. Well, for the first one here, reflective across the y-axis, that doesn't do anything, because we just get negative x cubed plus 1. Well, are these the same? Well, that's still a definite no. Would we agree there? Here, if I add 1, well, that means I'm going to have to divide by 1. I know I'm doing this real shorthand. That gives us negative x cubed minus 1. Well, these here are definitely still not the same. If we add 1 here, I still have to divide by negative 1, which makes it, is the one for the origin the same as what we started with? No, because as soon as I added 1, it's not reflective across the origin anymore. We moved it. Does that kind of make sense? So it's not guaranteed that every cubic function is going to be symmetric to the origin, but the parent function y equals x cubed is. And this is similar with quadratics. If we move a quadratic up or down, it is going to be symmetric to the y-axis. But if we move it left or right, it's not. And one thing that comes into this is even and odd functions. Even and odd functions. And this is still talking about really symmetric to the y-axis and symmetric to the x. Because if we look at this first one here, if f of negative x is equal to f of x, what are we doing? We're taking all the x's and replacing them with negative x. That is our test for symmetry across the y-axis. So if it's symmetric across the y-axis, it's most likely going to be an even function. For odd functions, if we take f of negative x, and it's the same as negative f of x, then it's going to be an odd function. And these here, I do these for especially testing with even and odd functions. I do them in a similar method. Well, so really, even is symmetric across the y-axis. Odd function is really going to be a symmetric across the, make sure, no, across the origin, not x-axis. Yeah, that felt a little weird. Origin, kind of our y equals x. So it'll be a flip across both, across the x and y. So if we look at these three here, if it is reflected across the y-axis, this point 1, 1 should be symmetric to negative 1, 1. We can flip it right across the y-axis. So we're really just changing the x value. Well, you can see that's not true. But the origin is really changing across both. That we would flip 1 here and then down here. Well, these two are symmetric across this here. Can we kind of see this here? For the most part. Now, we can look at the graph of it. Now, in the graphing calculator, it's going to be a little weird trying to plug this in. Or actually, that should be it. We get this function here. Now, with respect to the origin, it's just saying that it's reflected across the line y equals x. As here, we can see the flip from one to the other. Because if we rotate it across there, we would get it over and back. But, see this. We do get this here. This is reflected across the origin. Essentially, we're flipping both the x and y values and getting this here. Questions on this so far? Now, if we look at the second one, well, it's definitely not going to be reflected across the origin. We're not flipping both, but all the points on this do mirror each other across the y-axis. So this would be considered even. If we look at this last one here, this would be, it's not across the y because they're not over here, and they're not across both, they're not coming down here, so this is neither. Because they don't have to be even or odd function. There's a lot of functions that are neither even or odd, because it could be neither. Questions on any of this here? Are you ready for the next one? Determine if the function is even, odd, or neither. Now, the first place I always start out with is f of negative x. That's the first one I always look at if we're talking about the function. Because for it to be even, f of negative x is going to have to equal f of x. We already have f of x. That's the starting function. So f of negative x is just saying we're replacing every x value with negative x. We have negative 2, parentheses, negative x to the fourth, plus 5 times the absolute value of negative x. Now we need to simplify our absolute values in parentheses. Now negative x to the fourth, we're multiplying negative x by itself 4 times. Well, the negative is going to become positive. And we'll have x to the fourth. And we went over this a little bit in Algebra 2, especially when we were talking about Descartes' rule of signs. If the power for these here, these negative x's, is even, the sign stays the same. Since it's a negative, it stays negative. If it had been odd, we change the sign. Plus 5 times, well, as we see here, because it's just the absolute value of negative x, that negative is going to become positive. So it's the same as saying just the absolute value of x. Because if we had plus 1, we'd have to leave it as negative x plus 1, the absolute value of negative x plus 1. But since it's just by itself, this is the same as the absolute value of x. So are these two here the same? Oh yeah. So that tells us that this is considered an even function. Now, if we wanted to test if it's an odd function, we need to find out what negative f of x is. Negative f of x. Now, negative f of x, all that's saying is that we have negative times, negative 1 times the function f of x. Well, our function f of x is negative 2x to the fourth plus 5 times the absolute value of x. And if we distribute this negative, negative 1 times negative 2x to the fourth is just going to be 2x to the fourth. Negative 1 times, bless you, 5 absolute value of x is going to be negative 5 absolute value of x. Is this the same as our original function? No. So we did say the function is even. So what that means for us is that f of negative x is equal to f of x. This is true. But it's not odd because negative f of x is not equal to what? I think it's an, okay. Yeah, negative f of negative x. F of negative x. Or really in that case, which was the same as f of x, so this, again, is not odd. So really they wanted to compare these two, not the original. I got that flipped. But any questions on this so far? Now, for the most part, if a function's even, most likely it's not going to be odd. If a function's odd, it's not going to be even, and there is the chance that it could be neither. Any questions on this here so far? Let's look at the next one, B. So we have what g of x is. Now if g of x is equal to g of negative x, then it's going to be even. And if negative g of x is equal to g of negative x, negative g of x is equal to g of negative x, then it is odd. And if neither one of these is true, then it's going to be neither. So the first place we can start is seeing what g of negative x is. Because once we find out what g of negative x is, then we can see what the function is. And all this requires us to do is plug in negative x for every x that's in the function. So we get 4 times negative x to the third minus negative x. Well, negative x to the third, well, a negative times a negative is a positive, times a negative is a negative. So this 4 is going to become negative 4, and we still have our x to the third. Minus negative x. Well, the negative and negative will make a positive. So is g of negative x the same as g of x? Are these the same? No. So we cannot say that g of x is equal to g of negative x, which means it's not an even function. So it's not going to be symmetric to the y-axis. Now the next thing we need to find is negative g of x. Now negative g of x I think is a little bit easier to find than g of negative x. Because for this here, all we're saying is that we're distributing a negative through the entire function. We're multiplying everything by negative 1. So our negative 1 times 4x cubed is going to be negative 4x cubed. Our negative times negative x is going to be plus x. Now for our odd, negative g of x needs to equal g of negative x. Are these two equal? Are these two the same? Yes. So that means this function is odd, or it is reflective across the origin. Yep. Because if we plug negative x in for x, and it's the same as the function we started with, it is even. If that's not true, and we multiply the whole function by negative 1, and that multiplication of negative 1 is the same as when we plugged in negative x, then it's considered an odd function. And if neither one of these is true, then it's going to be neither. Now we can look at C, h of x. Now for this to be even, h of x needs to equal h of negative x. And for this here, we'll plug negative x in for every x's spot. So the first one we have is negative x squared, which is just going to be x squared. Because negative x times negative x is positive x squared. We can plug it back in. We multiply it by 2. Plus negative x is just going to be negative x. Is 2x squared minus x the same as our original function? No. So h of x is not equal, is not the same as h of negative x. So that tells us it's not an even function. Now for it to be an odd function, negative h of x has to be the same as h of negative x. So we need to find negative h of x, which is just really multiplying the entire function h of x by negative 1. And if we do that, we multiply both of these terms by negative 1, we'll get negative 2x squared minus x. Now, is our h of negative x the same as negative h of x? No. So this one here is neither. This one here is neither. Questions on any of this here? Are you ready for the next one? Evaluate the function for the given values of x. So the last thing we're talking about in this section is piecewise functions. Piecewise functions like this one here. And whatever value we're given is going to determine which function we use. Because if the values of x that we're plugging into this function are less than negative 1, we use the top one. We use this top function here. So if the values of x are less than negative 1, we're going to use the function negative x minus 1. If the values of x are equal to negative 1 or less than 2, between negative 1 and 2, then we use the function negative 3. And if the values of x are equal to 2 or greater than it, then we use the last function, the square root of x minus 2. Because whatever values of x are going to depend on which function we use. Now, if we look at the first one here, we have f of negative 3. So is negative 3 less than negative 1, between negative 1 and 2, or greater than or equal to 2? Well, it is less than negative 1, so we use the function negative x minus 1. And for us here, we'll use that function, negative x minus 1, and we replace x with its value. And in this case, x is negative 3. Well, negative 3 is positive 3, and 3 minus 1 is 2. So f of negative 3 for this function is positive 2. And that's it. Questions on this here? Now we can look at the next one, f of negative 1. And we can start at the top. Is negative 1 less than negative 1? No. Negative 1 is not less than negative 1. We can look at the next one. So the next one is negative 1 is less than or equal to x is less than 2. Is this true? Yeah. The negative 1 fits in the middle one here. So this is equal to negative 3. Because when it's just a number, we have a horizontal line, so all the values between negative 1 and 2 equal to negative 1 will all have a value of negative 3. Any questions on A or B? Let's look at C, f of 2. Now, we know that the first one's not true. The middle one does have x is less than 2, but it's not equal to it, so we're not going to use that one. We'll use the bottom one because it's greater than or equal to 2. Now, unlike the last problem where it just had a number, we do have an x value here. And we'll replace that x value with 2. So we get the square root of 2 minus 2. Well, 2 minus 2 is 0, and the square root of 0 is 0. So for this piecewise function, when we find f of 2, its value is 0. Any question on A through C? And the last one is D. And which one, the top, middle, or bottom one, which function would we use? We'd use the bottom one because it's the one that makes our inequality statement true. And we're going to replace that x with 6. Here we'll have 6 minus 2, which is 4. And the square root of 4 is 2. So for this function here, f of 6, its value is 2. Questions on any of this here? Now, we do have a few 4 or 5 minutes left. I'm going to stop here because I think we can get most of the way through this, but I want to give you guys time tomorrow. We're going to go over this tomorrow. We'll do this one and the next one, and that, I believe, is I think there's one more, but that's going to be the end of the note sheets. Then you'll have the rest of the time in class tomorrow to work on the review. We'll go over it Friday, and then unfortunately your test will be Monday.